Okay, so let's continue on the functional linear models. So we know there are three type of functional linear models. The first one is the response is the scalar, and the covariates are functions. So this is the scalar to functions linear models. There, the second one is the response is function, and the covariates are scalar. So we have the function on scalar for linear models. And last one, most complicated one, are both the response and the covariates are functions. So we call it function on function linear models. So among functional linear models, there are also two type of functional linear models. One is called concurrent models, which is show you here in these equations. So basically, the value of the response y will only depend on the value of x at the current time t, so the same time. So we call this as the concurrent models. Okay, so we also learned a more general one, which is the response y at time t will depend on the x on the whole time range. So here, this is the second type of functional linear function models. And so here, this x is a function, and so the range of this s will range on the whole time intervals. So here, the value of beta st represents the effect of x at time s on the value of y at time t. Okay, so here we have a bivariate coefficient beta s of t. So we have learned about how to estimate these bivariate functions. So basically, we will represent these bivariate functions as a linear combination of bivariate basis functions. And so to construct these bivariate basis functions, we use the tensor product of two one-dimension basis functions here. So to derive the estimation, we have to using the Kroneck product for this estimation in the formula. So we also talk about the confidence intervals. So although these models looks complicated, but in the end, we can still able to retain the coefficients as a matrix times the basis coefficient for the y. So here, this big matrix we call the C2B map, and so if we have this form, then we can express the variance of B hat as this using kind of this delta method, like so basically it's the C2B map times the variance of the C times the CB map transpose. Okay. So so this show like the common interval for the intercept here. So the intercept here is also a function beta 0t, and we can also come with the common interval for the bivariate coefficients beta s of t. And so here, this red surface represents this 95% common interval. It is hard to see too much things here. The reason is because I think these bivariate functions coefficients are too bumpy here, and it's hard to interpret this. So in order to control the smoothness on the bivariate coefficients, we also can include the smoothing penalty on the bivariate coefficients. So this is the general function on function linear models. So we can put a more general function linear models. In time series, we have learned called AR model, right? So for AR model, basically means the value of the current time will depend on the value in the previous R time points. Okay, so here we also have a functional version of the AR models. So this will be the functional version of the AR models. So basically here so you can understand like as a year. Okay, so if you look at this in our Sweden mortality examples, so this YIOT will be the hazard function at the year I. Okay, so then the hazard function at the year I will depend on the previous 1 to k years. Okay, so here yi minus j will be the hazard curve from I minus 1 to I minus k. Okay, so this is the functional version of the AR models. Similarly, you can also come with a functional version of ARMA models. So in time series, we also have the ARMA models. So here, in these models, YIOT will not only depend on the I minus 1 to I minus k, the hazard curves. It also we have this residuals epsilon I of t, and also this epsilon I minus 1 to epsilon I minus q of t. Okay, so this is kind of can consider this correlation among these residual curves. Okay, and similarly, you can also come up with some partial equation models when you consider the derivative of the curve on the left side. Okay, so this is some general versions of functional function linear models. Okay, so there's a whole research area talk about how to dealing with this functional time series. So in this case, in a time series at each time point will not be a vector, will be a function there. Okay. A more useful restrictions on the function linear models is we call a historical linear models. Okay, so for historical linear models, so before this is very similar to the model we used before, but before when we look at these linear models, the range of the integral is for the whole time interval. It's like for example, if the time is between 0 to 1, the range will be from 0 to 1. Okay. So there's one problem if we look at the integral over the whole range, is that so basically this beta 1 s of t represented the effect of the value of y at time t on the value of the x at time s, right? But if you think about, for example, when s is greater than t, so in other words, you will look at the value of yi at time t depend on the future values of x at time s, right? When s is greater than t. This didn't make sense, right? So in reality, we think definitely the value of current y will only depend on the value of x in the history, not in the future, right? So this is one potential problem for general function models. That's the reason we can put the range of this integral from 0 to t instead. So if you put this range in this form, then the s will only between 0 and t. S will always be less than t, right? So then this model will be more realistic, right? Yes. So the value of the yi at time t only depends on the value of x before t. Okay. So this is the we call it historical linear models. Okay. So there's another versions. We can even put them these more restrictions. For example, we often think the value of y at time t will only depend on the value of x before t, but this effect may there's maybe no effect at all after certain time lag. So for example, let me give you one example. Like suppose here the response y is the forest fire. Okay, the amount of forest fire at time t, and the x, suppose this is the temperature of the rainfall of the at time s. Okay, so we may think the amount of forest fire will depend on the rainfalls only like up to 1 month, right? If you think about if there's a too long lag, there will be no effect. For example, the current forest fire will not depend on the rainfalls in 100 days, for example, maybe, right? Because whether there's a rainfall in 100 days before, there will be no effect on the condition of the forest fire at the current time, right? So therefore, we will also have restrictions on the s. So s can only go from t minus delta to t. Okay, so this delta will represent the lag effect. Okay, so in other words, the forest fire at time t will only depend on the rainfalls before delta days, right? So if it's more than delta days, then there will be no effect on the forest fire, right? So this is definitely a very realistic and interpretable models, right? Okay, so this is another models. This model called functional convolution models. Okay, so for this type of models, this is more realistic, but the estimation actually is harder than the general functional linear models, because if you think about, for example, for the historical linear models, the beta 1 s of t can only be 90 when s is less than t. So, for example, if you draw a picture about the beta s of t. So if this is t and this is s, and so suppose the color here represents the value of beta s of t. So beta s t will only be 90 when s is less than t, right? When s is less than t. So so this is s equal to t, right? So when s is less than t means so only this part, the beta st will become 90, right? So in the up triangle, there will be the beta s of t will become strictly 0, right? Yes. So therefore, when you do the estimation, you cannot use the tensor product, because when we do the tensor product, basically the tensor product is divided this range as some small square, right? So this is when you do the tensor product. Basically, each basic functions will represent this the value of this beta st at this small square or rectangle. But for this one, if you're using this tensor product, then you will have a problem on this diagonal part, right? That's a problem. So therefore, when you have these restrictions you may using other basic functions like triangular basic functions. Basically, now you will not look at this tensor product. So instead, your basic functions will be working on only on the triangle. Like so, for example, like here, these triangles. So something like this. Okay, so only the triangle part will become have this support. Okay, so this is called triangular basic functions. Is also some part called partial linear. Finite element method. Okay, so this will be more complicated than this tensor product to construct the bivariate basic functions. And for the functional convolution models, it will even be more complicated because if you think about so for functional linear models, basically the value of beta s of t will only become non-zero when s is between t minus delta to t, right? So suppose this is s equal to t, this is st minus delta. So basically, suppose this is the range, right? So this is the delta, right? And so this will be this curve will correspond to s equal to t minus delta. So this should be parallel with the diagonal part, right? So this is delta, this is delta. Okay. So then the beta s of t will only be non-zero in this range. Okay. Yeah. So in that case, you will have more restrictions, and when you do the estimations, you have to be more careful when you do the estimate beta 1 s of t. Okay. So this is the two restricted functional linear models. So here is the summary of what we learned. So basically, when we learned these function linear models, so we need to estimate these bivariate coefficient functions. So that's definitely the computation and the formula will be more complicated. And also for these function linear models, there's a direct extension on the time series. We call it a functional time series. When at each time we'll have a function instead of just a number. And we also learned the restricted function linear models. These are more useful, but it's harder to code because you cannot use in the tensor product of the universal basic function anymore.